Welcome to Quantum, the channel where we delve into mathematical, theoretical, and philosophical physics, exploring everything quantum. In this video, we embark on a comprehensive journey through atomic physics, focusing on Bohr's atom, one of the most foundational models in quantum mechanics. We begin with angular momentum and motion on the sphere, uncovering how quantum mechanics constrains orbital motion. Next, we solve the central problem and derive Bohr's energy levels, providing a rigorous proof of energy quantization. We then introduce the harmonic oscillator formulation of the hydrogen atom, offering an alternative perspective that makes quantization inevitable. We then explore spin-orbit coupling and fine structure corrections, revealing the relativistic effects that shape hydrogen's energy spectrum. Moving beyond fine structure, we analyze the hyperfine structure, Stark effect, and Lamb shift, introducing quantum electrodynamics corrections. Finally, we conclude with the Zeeman effect, where external magnetic fields alter atomic energy levels in a strikingly measurable way. Each of these topics plays a pivotal role in quantum mechanics and atomic physics, connecting fundamental principles to real-world experimental phenomena. Let's dive in. Angular momentum, spherical harmonics, and addition of angular momentum. In the first section, we provide a mathematical proof of the quantization of orbital angular momentum in quantum mechanics. We solve the equation for a particle on a sphere, where the solutions are functions on the sphere known as spherical harmonics. This problem represents the angular part of the hydrogen atom and applies to any other central problem. Then, in the second section, we briefly introduce the theory of addition of angular momenta. Specifically, we provide a detailed presentation of the Hilbert space associated with the total angular momentum, orbital plus spin, which plays a crucial role in the hydrogen atom. Central problem and Bohr's atom. Having solved the angular part of the hydrogen atom in the previous section, we now turn to the radial part in the third section. Specifically, we derive the energy levels of the hydrogen atom, widely known as Bohr's energy levels, and present a detailed proof of energy quantization, a result of profound significance in physics, theoretical physics, quantum mechanics, and atomic physics, both in terms of its objective impact, historical importance, and educational value. Additionally, we derive the orbital wave functions and demonstrate that they are governed by Laguerre polynomials. As a reminder, in the first section, we established that the spherical harmonics, which describe the angular part, are determined by Legendre polynomials. Bohr's hydrogen atom as a harmonic oscillator problem. In the fourth section, we delve into the fundamental physical reason behind energy quantization in the hydrogen atom, which I personally prefer to call Bohr's atom. To begin, we recognize that the probability of finding the electron at any point in space must be finite, a condition that serves as the mathematical justification for quantization, as derived in the previous section. However, this alone does not suffice as a physical explanation, as it merely results from the requirement that the total probability of the electron existing somewhere in space must be 1, a consequence of Born's statistical rule. While this rule is crucial, it does not fully account for the physical origin of quantization. The true physical foundation of energy quantization in the hydrogen atom lies in wave-particle duality, most precisely expressed through Heisenberg's uncertainty principle. Wave-particle duality implies that the electron within the hydrogen atom fundamentally behaves as a wave. Building on this, we introduce a rarely discussed result in standard quantum mechanics and atomic physics textbooks, where we reinterpret the hydrogen atom as a harmonic oscillator problem. More specifically, we demonstrate that Bohr's atom is equivalent to two coupled harmonic oscillators in 2 dimensions, with the constraint that their total angular momentum is 0. By formulating the hydrogen atom in terms of a harmonic oscillator, we can directly express the fundamental commutation relations that govern the quantization of phase space. These commutation relations naturally lead to Heisenberg's uncertainty principle for the system's variables, making the connection between wave-particle duality and energy quantization in the hydrogen atom explicitly clear. Furthermore, we explicitly show how energy quantization in the hydrogen atom emerges naturally from its harmonic oscillator formulation. The spin-orbit coupling and fine structure of hydrogen. After deriving Bohr's energy levels of the hydrogen atom in the previous sections, where we found that these levels depend on a single quantum number, the principal quantum number, we now proceed in this lecture to compute the most significant perturbative correction to these energy levels. Since perturbation theory plays a central role in this analysis, we begin in the fifth section with a brief overview of the three key results from quantum mechanical perturbation theory that we will require. First-order correction in non-degenerate perturbation theory, which is generally straightforward. First-order correction in degenerate perturbation theory, which is significantly more complex. First-order correction in degenerate perturbation theory in the presence of symmetry. In this case, we show that we can instead apply the simpler non-degenerate perturbation theory, provided that we perform the calculations in what are known as good quantum states. Since this is an atomic physics course, not a quantum mechanics course, these results are stated without proof. In the sixth section, we begin the calculation of the most crucial correction to the hydrogen atom's energy levels, known as the fine structure of the hydrogen atom. This correction is the most important because it represents the largest energy shift in magnitude. The fine structure of the hydrogen atom arises from two fundamentally different physical effects within quantum mechanics. Relativistic correction. This results from the high velocity of the electron inside the hydrogen atom. Despite the common perception that relativistic corrections are difficult, this correction is actually straightforward to compute. Spin-orbit coupling. This arises from the interaction between the electron's spin angular momentum and its orbital angular momentum. Computing this correction is significantly more challenging. To understand spin-orbit coupling, we must recognize that in the electron's rest frame, this effect originates from the interaction of the electron's magnetic dipole moment with the proton's magnetic field. However, the electron's frame is non-inertial, making the computation more complex. On the other hand, in the proton's rest frame, which corresponds to the laboratory frame, an inertial frame, this correction arises from the interaction of the electron's electric dipole moment with the proton's electric field. Interestingly, even though the electron's frame is non-inertial, it is actually easier to perform the calculation in this frame because handling magnetic fields is often, contrary to intuition, simpler than dealing with electric fields. Thus, we begin by calculating the interaction energy between the electron's magnetic dipole moment and the proton's magnetic field, which is found to be proportional to the electron's orbital angular momentum. Next, since Bohr's energy levels are degenerate, we must apply degenerate perturbation theory to compute the energy correction due to spin-orbit coupling. This is inherently a complex procedure. Fortunately, the system possesses rotational symmetry, allowing us to define good quantum numbers for the system. This enables us to use the simpler non-degenerate perturbation theory, provided that we work in the basis of good quantum states, which are the eigenstates corresponding to these quantum numbers. The good quantum numbers are precisely the eigenvalues of the symmetry-related operators associated with rotational invariance. While this approach simplifies the computation somewhat, it remains a highly non-trivial task. After completing all calculations and summing the relativistic correction and the spin-orbit coupling correction, we obtain the fine structure, one of the most precise and remarkable predictions of quantum mechanics. For instance, we find that Bohr's energy levels no longer depend solely on the principal quantum number. Instead, they now also depend on the total angular momentum quantum number, which accounts for both orbital angular momentum and spin. The hyperfine structure, Stark effect, and Lamb shift. In sections 7 and 8, we compute three additional perturbative corrections to the hydrogen atom, the hyperfine structure, Stark effect, and Lamb shift. In section 7, we examine the first correction, known as the hyperfine structure of the hydrogen atom, which results from the interaction between the spin angular momenta of the electron and the proton. In this correction, the total spin wave function, comprising the electron spin and proton spin, splits into two energy levels: the singlet state, which is non-degenerate; the triplet state, which, as the name suggests, is degenerate and consists of three states with the same energy. Although the hyperfine structure correction is smaller in magnitude than the fine structure correction discussed in the previous section, its significance lies in cosmology. The transition between the singlet and triplet states corresponds to a highly significant electromagnetic wave known as the 21 centimeter line, named after its actual wavelength of 21 centimeters. This wavelength dominates the microwave background radiation of the universe from the epoch of recombination, when hydrogen first formed, to the epoch of reionization, when the first stars were born. During this period, from approximately 400 million years to 1 billion years after the Big Bang, the cosmic microwave background (CMB) radiation was primarily composed of this 21 centimeter emission. In Section 8, we examine the Stark effect, which describes the behavior of the hydrogen atom in the presence of a uniform electric field. This effect is of fundamental importance in experimental physics, just as the hyperfine structure correction is crucial in cosmology. Additionally, we introduce the Lamb shift, a well-known correction named after physicist Willis Lamb, who experimentally discovered this phenomenon and was later awarded the Nobel Prize for his work. The Lamb shift arises due to the quantization of the electromagnetic field and, more precisely, is explained by Feynman diagrams which account for vacuum polarization, a correction to the photon wave function; mass renormalization, a correction to the electron's energy; vertex correction, a correction to the electron's magnetic moment. The 1947 discovery of the Lamb shift was the primary catalyst behind the rapid and dramatic development of quantum field theory, QFT, and the subsequent rise of particle physics as the dominant field in theoretical physics. Zeeman effect. In the last section, we introduced the final perturbative correction to Bohr's energy levels, the Zeeman effect. The Zeeman effect describes how the hydrogen atom behaves under the influence of an external magnetic field. As previously mentioned, magnetic fields are far more significant than electric fields, making the Zeeman effect more important than the Stark effect, which we discussed in a previous section. The significance of the Zeeman effect lies both in experimental physics and in natural astrophysical processes, as it can occur purely in nature. For instance, magnetic fields in interstellar space, within and between galaxies, induce energy level shifts in atoms, a phenomenon predicted by quantum mechanics. Unlike the fine structure correction, where spin-orbit coupling arises due to an internal magnetic field generated by the proton in the electron's frame, the Zeeman effect is induced by an external magnetic field. This leads to different regimes based on the relative strength of the external and internal fields. Case 1. Weak external magnetic field. If the external magnetic field is much weaker than the internal magnetic field from spin-orbit coupling, then spin-orbit interaction dominates. In this regime, the external magnetic field can be treated as a perturbation. The good quantum numbers remain the same as those in the fine structure correction. We apply non-degenerate perturbation theory, working in states labeled by these quantum numbers. Using the Wigner-Eckart theorem, we find that the correction is proportional to the Landé factor. This result shows that although the total magnetic moment of the electron is not directly proportional to its total angular momentum, their expectation values are indeed proportional. Case 2. Strong external magnetic field. If the external magnetic field is much stronger than the internal magnetic field from the proton, then the Zeeman effect dominates over spin-orbit coupling. In this case, the external magnetic field cannot be treated as a perturbation, but must instead be included in the unperturbed Bohr energy levels from the start. The good quantum numbers in this regime are those associated with the unperturbed Bohr atom. We apply non-degenerate perturbation theory, working in states labeled by these quantum numbers. Since the nature of the good quantum states changes, the fine structure correction must also be recomputed accordingly. Case 3. Intermediate magnetic field strength. If the external magnetic field is neither very weak nor very strong, the situation becomes far more complex. In this intermediate regime, we must apply fully degenerate perturbation theory in its strongest form, making the calculations significantly more challenging. Conclusion. From angular momentum quantization to the fine structure of hydrogen, we've uncovered the deep mathematical framework that governs atomic physics. Bohr's model may be an early quantum breakthrough, but its principles extend far beyond, connecting symmetry, wave mechanics, and even quantum field theory. If this deep dive into atomic physics intrigued you, be sure to like, subscribe, and comment which aspect of quantum mechanics fascinates you the most. Subscribe to Quantum for more in-depth explorations into the mathematical, theoretical, and philosophical foundations of quantum physics. Until next time, keep questioning the quantum world.